So thanks, Lawrence, for the very kind introduction. So I'm indeed going to be talking about elliptic curves, about isogenies and endomorphism rings. The main point of view that I'm taking is that it's very interesting in crypto, and I want to give you some flavors of the problems or of the way that elliptic curves make their appearance in isogeny-based cryptography. But let's start with elliptic curves, and we're only going to be talking about elliptic curves over finite fields. So an elliptic curve over a finite field of Q is an algebraic group. So it's given by an equation. It's given by a cubic equation, y squared is xq plus ax plus b, where a, b are some constants and there's some non-degeneracy condition. And so that means that it's an algebraic variety. And it has some points, and points of the elliptic curve are pairs x and y in the algebraic closure that satisfy this equation. Together with these points, we have this point at infinity that comes from the projective closure of this equation. And I said that it's an algebraic group, so that means there's a group law, and the point at infinity is the neutral element for this group law, and the group law is given well, both algebraically and geometrically. Geometrically, it's easy to describe. 3 points sum up to the point at infinity, if and only if they lie on a line. So here you have 3 points on an elliptic curve, and they all lie on a line, which means that these 3 points sum to infinity. Okay. There's also a way how to write down these the formulas for the group law, but we will not need it for anything. It's just good to keep in mind that if you want to add 2 points, there's a formula for it, and the formula is defined, only uses the coordinates x and y and the coefficients a and b. Okay, so what we also need to know, and mostly we'll talk about today, are these rational points. So the rational points form a subgroup of the elliptic curve, and the subgroup includes this point at infinity, that's the neutral element, and points of E, both of the curve coordinates of which are in FQ, so in the finite field FQ. And so here you have a picture of rational points of this elliptic curve over the finite field with 37 elements. So just, you take in some x and some y, and you plug it into this equation. If you get equality, it's a point. Okay, so these are the rational points, and it's a subgroup, and this is the subgroup we will mostly talk about. Okay. So still talking about elliptic curves, and they are given, I told you that there are algebraic groups and that they're given by this equation. This equation is in general not unique, so we need some better ways how to distinguish different elliptic curves, and for that we use the J invariant. So J invariant is just some number that you compute from the equation of the elliptic curve. And the great thing is that it's a FQ bar isomorphism. So if you have 2 elliptic curves that are isomorphic as algebraic groups, then they will have the same J invariant. Okay. And one more thing that we need to know about rational points is that by Hasselblad's theorem, every elliptic curve has about Q plus 1 points. Then there's some error term, and this error term is bounded by an absolute value by 2 squared of Q. Okay, so every elliptic curve has about Q plus 1 rational points. And now, what you might have heard about ordinary supersingle elliptic curves, then ordinary elliptic curves are the ones where P does, the characteristic of the finite field does not divide the error term T, and supersingular elliptic curves are those where P does divide the characteristic of T. So I will sometimes use these terms ordinary, supersingular. Okay, and what is useful about the J invariant is that actually curves with the same J invariant are either all ordinary or all supersingular. So I will also say sometimes supersingular J invariant or supersingular ordinary J invariant. Right. And so now I'm going to talk about isogenies. So isogenies are maps of elliptic curves as algebraic groups. So first of all, they're algebraic maps. They're given by rational maps. And they're also a group homomorphism. And we will assume that the rational maps always have this very simple form that x point with coordinates x and y maps to some function of x, and for the x coordinate and new y coordinate is just the old coordinate times some function of x. Okay, this doesn't we don't lose any generality, but it really simplifies the notation. So an example of an isogeny is of course the multiplication by m map. Any group has this self map where you take a point and you multiply it by an integer m. Okay, so this is an isogeny because the group law is given by algebraic formula. You can just figure out what the self multiplication is. And isogenies, because they're rational maps, they have some degree. So here we have an example of multiplication by 2. It's a degree 4 map because this expression is a degree 4 expression, so degree 4 rational function. And this is the multiplication by 2 on any elliptic curve. So it depends on the coefficients a and b of the elliptic curve. And as you see here, this expression has a denominator. So it's not defined at points of e for which this denominator vanishes. And so the points where the function is, the rational functions are not defined, plus the point at infinity, that's the kernel of the isogeny. And from this setup, it's clear that kernels always have to be finite because we only have finitely many solutions, finitely many points that satisfy this equation. And conversely, you can read off the kernel from the denominators of your isogeny. So now an example. We'll be talking about M isogenies or L isogenies. So if the isogeny has degree M, we just call it an M isogeny. And here we have an example of isogeny of degree 5, so 5 isogeny, because this rational function is degree 5. And if we want to figure out the kernel, then we just look at the denominator and see what are the points of E where the denominator vanishes, and this gives us this kernel. We need to include a point at infinity. And lo and behold, the kernel has 5 points, and it was a 5 isogeny, and that's not a surprise, because if the characteristic does not divide the degree, then the degree is exactly the number of points in the kernel. Okay? So you can also think of the degree as typically being the size of the kernel. Okay. What else do we need to know about isogenies? Well, I told you that they're homomorphisms of elliptic curves. And you know that if you have a homomorphism of groups, and you have a subgroup, you can quotient out by the subgroup. And this is the same for elliptic curves. Whenever you have a finite subgroup, you can construct an isogeny that has subgroup as its kernel. And we will write that the target is just E mod H. And the beautiful thing about this is that you can actually write down the isogeny and the equation for the target curve if you have an explicit description of the subgroup. So here you see the values formulas that if you see the points in the kernel, then you can compute the formulae and you can compute the equation. So this is a pretty complicated expression to write down, but here's an example. Here we have the elliptic curve given by y squared is x cubed minus x. And here you have the point 0, 0. So it generates some subgroup, this. And if you want to figure out what's the curve E mod this subgroup, well, if you use values formulas, this is exactly what you get. The isogeny is given just by sending x and y to these very simple expressions. And the equation of the target curve is this. Just y squared is x cubed plus 4x. Okay, so values formulas is you can think of it just as a tool. If I have a description of the kernel, I can compute the isogeny. Okay. One more thing, and this is more of a side note, is that for any isogeny going from E to E prime, there exists a dual isogeny going the other way. And if you first go by from E to E prime by phi, and then take the dual isogeny from E prime to E, you only get multiplication by the degree. So in some sense, dual isogenies are not as interesting, because if you compose with your dual, you always just get multiplication by a scalar. So in the coming, we will typically just identify an isogeny with its dual, just because if you compose with your dual, you just get multiplication by a scalar, and that it's not such an exciting isogeny. Okay, so we had the just to show you again, if you have an isogeny and you have a good description of the kernel, it's very easy to figure out what the dual isogeny is supposed to be. Okay, and now we come to another important topic. So we had elliptic curves, isogenies, and now we're doing endomorphisms, and then we're almost done. If you have an elliptic curve, there are interesting isogenies that go from the elliptic curve to itself, and those are the endomorphism rings. And we will only study this rational endomorphism ring, so only isogenies defined over the base field FQ. If we add the 0 to it, then we have a ring structure. So we can multiply isogenies by composing them, and we can add isogenies because we can add homomorphisms. And the most important isogeny or endomorphism is the Frobenius endomorphism. And for an elliptic curve E over FQ, it's given by taking a point with coordinates x and y and raising them to the power q. Okay, so you see that this is an endomorphism. It's an isogeny of degree q. Okay. And why is it so important? Well, if your elliptic curve over FQ has q plus 1 minus t rational points, then t is what's called the trace of Frobenius. And what is even more miraculous is that if you take pi squared, the Frobenius squared minus t times Frobenius plus q, where the t and q are the t and q from the number of points, then you get 0. Okay, so the Frobenius is so important because its properties are intimately tied with the structure of the rational points. Okay, so let's continue with this. So we have this Frobenius endomorphism that satisfies this quadratic equation, but hey, from Hasse-Weil, we knew that the t, this trace, was bounded by 2 square root of q. So the discriminant of this quadratic is at most 0. And now we have this beautiful split for what can happen if the discriminant of the quadratic is actually negative, then pi as a solution to this quadratic equation lies in an imaginary quadratic field. And what's the statement that you have to prove is that the whole rational endomorphism ring actually embeds into this imaginary quadratic field. And it's easy to show then that this imaginary quadratic field is generated by the square root of t squared minus 4q, so square root of the discriminant of the quadratic. And the rational endomorphism ring embeds there as an order. Okay, so if you don't need to know what it is exactly, but if you've heard about maximal orders, then it's just a slight generalization. Now, if the discriminant is 0, then you can actually solve for, so then this quadratic has a repeated root, and you can solve for this root, and it's then pi is plus minus square root of q, and in this case, the rational endomorphism ring actually embeds to a quaternion algebra which you can specify as ramified only at the prime p and infinity, and it also embeds as a maximal order. Okay? So this is just this big statement about how the endomorphism ring behaves. But the important thing is that if the discriminant of this quadratic is non-zero, then you're in this imaginary quadratic field, and the discriminant is 0, then you end up in a quaternion algebra. And so now let's go through some examples. We have this elliptic curve over the field of 31 elements. You ask Sage to give you the number of points. You figure out that the trace t is 6, and the discriminant you compute as minus 88. And by solving this equation, then you find that pi is 3 either plus or minus a square root of minus 22. So I told you that in this case, the rational endomorphism ring is an order in this imaginary quadratic field. And it needs to contain, of course, the subring generated by Frobenius, which is z adjoined with square root of minus 22. So this is an example of an order. But this is ordered in maximal order, and so you can figure out the endomorphism ring. Now, another example, same field, where we change the curve. And if you count the number of points, then you figure out that the trace is 0. And if you remember from the beginning, this means that this is a supersingular elliptic curve. But still, the discriminant is non-zero. So the rational endomorphism ring is an order in this field generated by Frobenius, generated by the square root of the discriminant. And as an exercise, you can show that actually the rational endomorphism ring is this maximal order. Okay, so now let's continue with a very different elliptic curve. It's given by the same equation, y squared is x cubed minus x, but now it's given over a different field. And Frobenius depends on the field that you define your curve over. Okay, so this is a different curve, a different situation. You count the number of points, and you see that the trace is minus 2 times square root of q, and the discriminant is 0. So actually, the endomorphism ring is a maximal order in the quaternion algebra, ramified at 31 and infinity. And you can actually write down what this endomorphism, rational endomorphism ring will look like. It's generated by 1, I plus j over 2, and 1 plus ij over 2, where I squares to minus 1, j squares to minus 31, and I and j anticommute. Okay, and this is actually one of the few examples where it's so easy to write down the full endomorphism ring of a supersingular elliptic curve. Right, and there's an exercise. This elliptic curve comes from the elliptic curve in exercise 2 just by extending the scalars. So it makes sense that the endomorphisms that were already defined over F31 have to be somehow a subring of this order in a quaternion algebra. And so an exercise is to convince yourself that you actually have this as a subring of this ring in the quaternion algebra. So now we're going to start talking about the orders or the endomorphism rings in some detail. And so we take an ideal, and from that ideal in the order, we can produce a finite subgroup. How do we do that? We take every element in the ideal is an endomorphism ring. So it has some kernel, and we take the intersection of all these kernels. That gives us a finite subgroup. And once we have a finite subgroup, we can take the isogeny, which has the subgroup as its kernel. And what happens actually is that the degree of the resulting isogeny is going to be the norm of the ideal, which is something that you need to prove, but it's not hard. So let's take an example of how this works. How do we construct these isogenies? Well, take prime L different from P, and then consider this ideal generated by L and pi minus 1. So we need to figure out what this subgroup is, the A torsion subgroup. And we do it by intersecting the kernels of all the elements. And it's enough to take the kernel of L. Well, that's the subgroup of L torsion points. It's the kernel of the multiplication by L. And we have the kernel of pi minus 1. And this is easy to compute because that's just the points that are fixed by Frobenius, which are the points such that x to q is x and y to q is y, which is the group of rational points. Okay, so this new torsion subgroup, which is the intersection of the L torsion points and rational points, is just the subgroup of rational L torsion points. Okay, and so now what happens? We have a good description of the L torsion. It's not so hard to show that actually as abelian groups, the L torsion just looks like two copies of Z mod LZ. And so if you want to figure out what part of this L torsion is defined over FQ, it can either be all of it, but then the kernel of the isogeny phi L needs to be the whole L torsion. And so the isogeny is nothing else but just multiplication by L. If the torsion is, if the rational L torsion is generated by some point, so if it's cyclic, then we can use Weylu's formulas, just take the point, generate the subgroup, and compute the L isogeny that has this point as its kernel. And there's also this case where there are no rational L torsion rational points, and then the isogeny is just the identity. So there are some cases where it's very easy to say what the action of this ideal actually does. Okay. And so now let's say some more general stuff about this action. Well, if you are in the case where the rational endomorphism ring is in an imaginary quadratic field, and you take an invertible ideal, then the target curve has the same endomorphism ring and trace. So invertible ideals and the isogenies corresponding to them preserve the endomorphism ring and the trace. And moreover, if you take ideals that are in the same class, in the class group, you get FQ isomorphic elliptic curves. Okay. So we will consider this set, LOT, which is just the elliptic curves with a fixed rational endomorphism ring and a fixed trace. And we will take them up to FQ isomorphism. And by the two facts above, if you act on, well, if you take any elliptic curve here and you compute the isogeny corresponding to an invertible ideal, then you end up with the elliptic curve in here. And the main theorem of complex multiplication says that if you take any two elliptic curves in this set, then there exists a unique class in the class group such that the curve E prime is the image of the isogeny corresponding to A. I should have written it differently. So if you take the ideal A, well, you take the class A, you take any representative, that gives you an ideal. You use the ideal to compute an isogeny from E, that gives you some target curve E prime, and we denote it by A star E prime. Okay, so this, again, one more time, you take an elliptic curve, you take an ideal, and you compute the target of the isogeny corresponding to the ideal. And the main theorem of complex multiplication tells you that if you choose two elliptic curves in LOT, then there's going to be a unique class in the class group that connects them like this. And another way how to say that is that the class group acts freely and transitively on the set of elliptic curves with the same endomorphism ring and the same trace. Okay, why is this interesting? Well, this is how isogenies appear in cryptography. Okay, and to do that, I need to explain to you how Diffie-Hellman exchange works. So imagine that you have Alice and Bob, And Alice and Bob want to communicate over an insecure channel. So anyone can see what's happening on the insecure channel here in the middle. And how they do that nowadays is that they agree on a group, abelian group, and they agreed on an element that generates the group, and it's going to be an element of known order. And how they're going to communicate? Well, they want to establish a secret. So Alice, they want to establish a shared secret. So what Alice does, she takes some random integer between 0 and n, and she computes the power of the generator. What Bob does, he takes a random integer between 0 and n, and computes the power of the generator, and then they swap these values. So Alice sends g to a to Bob, and Bob sends g to b to Alice. Okay, and then what Alice does, she takes the g to b that she received from Bob, and she takes the 8th power. Bob does the same with what he got from Alice. And in the end, if you compare g to b times a and g to a times b, they both share the value g to ab. Okay, so this is secure as long as discrete logarithms are safe. But mainly, this is insecure against quantum computers using Shor's algorithm. So what we use now, which has basically the same works almost the same way, is not secure against quantum computers, and that's why you would like to replace it. And one way how to replace it is the following. Suppose that Alice and Bob also not only have this group and the generator, but they also have a free and transitive group action. Okay, so a free and transitive group a group action just takes a point in the group and a point in a set, and produces another element in the set. Okay, and what makes it free and transitive? Well, if you choose any point in X, then you get a bijection between X and G. But X is just a set. It has no extra structure, and G is a group. So what you can do, you can compute in the group G and then act on an element, and that just gives you an element of the set. So somehow you're hiding all this information about possibly leaking information about the elements that you used or any other stuff. You're just hiding it by acting on some point in a set and producing another point in a set, so no extra structure. And this is how you can easily modify this group action, this Diffie-Hellman paradigm, that Alice does exactly the same thing, but then instead of sending G to A, she sends the result of the action G to A on some chosen element X. Bob does the same, and then when Alice receives G to B acting on X from Bob, she acts on it by her G to A, and then because this is a group action, well, then they both end up with G to A plus B that acted on X. So they end up with the same element in the set. Okay. So they end up sharing a slightly different element, but they still end up sharing, well, they end up sharing like a different element, but they still share the same thing. And moreover, because Shor's algorithm needs to be able to compute in the group, if Shor only sees the elements in the set, and he's not able to produce, given 2 points in the set, he's not able to produce a third element in the set, the algorithm no longer runs. So this has a chance of being quantum secure. And this is where commutative isogeny-based cryptography comes in, because I've just told you that from CM, we have a free and transitive group action of the class group of an order on the set of elliptic curves, just by taking an ideal class and an elliptic curve and producing another elliptic curve. And why is this so great? Well, you hide the structure of the class group, which is a very rich arithmetic object. It's beautiful. It's really a classical object just to study. And you take its lovely structure and you hide it just by using the set of elliptic curves. And there's no way to take two elliptic curves and combine them and produce a third elliptic curve. Okay, so that's what makes it quantum safe, where this is, it's still a debate of how safe it is. It has sub-exponential quantum complexity, so it's not as safe as we would like, but maybe this is going to be enough. Maybe it's not going to be enough. Maybe it's still not clear how viable this is going to be, but it's still a pretty good solution, or good way how to counter at least some not very powerful quantum computers. Okay, but there are some things that will not work. We can't really compute a class group if the class group is very big. So if you've seen previous talk, there are some limits to what you can compute. So if you just want to have a very large class group for lots of security, then you can't really compute a group, and so you cannot get a generator, and there may not even be a generator. But what you can do, you can sample with ideals of the class. You can sample ideals from the class group. That's very easy to do. Remember, the ideal is L generated by L and pi minus 1. Those were very, very easy to write down. And then there's this caveat that if you can't actually act with all ideals, because you need to compute the subgroup, you need to compute the isogeny corresponding to the subgroup. So if the norm of the ideal is too big, then you simply cannot compute it in polynomial time. Okay, and so the modern solution is to go back to the action of the ideals that I told you about, and remember that if the rational L torsion was cyclic, then the action was very easy to compute. All you had to do was to find a rational point of order L, know that it generates the whole L torsion in the situation, and then once you have the L torsion, once you have the subgroup generated by P, you just compute the L isogeny using values formula, and that's fairly quick if L is small. Okay, and so that's the modern setup for commutative isogeny-based cryptography. You look for setups where you have elliptic curves with lots of cyclic L torsions for lots of small primes, and you only work with these ideals. You don't work with the whole class group. You just work with ideals that look like this, and their products, where you have lots of these small you have lots of the ideals Li, so you can take very small exponents Ei, and then the action by this ideal is just going to be a sequence of the steps as above. So always when you have one, you always take one prime ideal from this product. You see that it's a ideal of norm L. What you do, you find a rational point of order L, you compute this isogeny using values formulas, and then you do the next step. So somehow the secrets are lists of these exponents that tell you how many steps of using these ideas you need to take. And so if you want to use ordinary curves, which is the work of De O'Keefe and Smith, it's hard to find curves defined over large fields. That would be where the group order would be divisible by lots of small primes. So you will only manage to find, say, a cyclic L torsion for, I don't know, 10 small primes at a time. Whereas if you want to use supersingle elliptic curves, then you have as was done in Seaside by Bernstein, Lange, Martindale, Panay, and Rennes. You have the advantage that the number of points on a supersingle elliptic curve is just p plus 1, and it's easy to find primes such that p plus 1 is divisible by lots of small primes. Okay. So it can be done. You can find setups where all the isogenies you ever need to compute correspond to just finding small rational torsion points. Okay, and so this leads us to the first isogeny graph. And right, so if we have an ideal generated by prime L and pi minus 1, you can ask what happens if you act by this ideal repeatedly. So first you act by L and you get L star E. Then if you act by L on L star E, because it's a group action, you get L squared star E. And if you keep going at some point, and after as many iterations as is the order of the ideal in the class group, then you end up getting with the same curve. You end up with the same curve. So repeated action from E cycles you back to E. Okay, and so we consider this L isogenic graphs over FQ, and the vertices are still the same elliptic curves as we fixed before, and they will be labeled by chain variance, and edges will be L isogenies. They will be up to equivalence, because here you identify FQ isomorphic curves, and they will be up to dual isogenies, because if you go by an isogeny and go back, you just get multiplication by L, and that's not an interesting isogeny. Okay, so the graphs that we will see are just these beautiful cycles. So this is just a toy example, but this is what you will always see. So if you have, if you look at 3 isogenies, you just have cycles. If you look at 7 isogenies, you have potentially different cycles. If you look at 11 isogenies, you have a different cycle altogether. And so one way how to think about C-side is that you, the secret, you just start the work in the following way. You start with some elliptic curve, and you walk on this cycle for a little bit, and then you just switch and you jump into a different isogenic graph, and you walk on a lovely cycle for a bit, and then you jump to yet another isogenic graph, and you walk for a little bit, and you do this repeatedly. So it's very easy for you to compute these actions and to compute your secrets. But if somebody wants to figure out what exactly you did, this is what they will see. They will not know which steps you exactly took. And moreover, if you, depending on which isogeny you take, it might take you to a completely different place in the graph. So if you start, say, at 127, you take the 7 isogeny, which is in green, you end up here. If you take a red isogeny, you end up here. And it's just not very, it's almost impossible to figure out which way you went. Okay, so this is just a visualization of what the security relies on. Okay, so far I told you about invertible ideals, and I told you that they preserve the endomorphism ring and the trace, and now the isogenic graphs that we saw were all just unions of cycles. And that means that from every elliptic curve, there were just 2 isogenies in every direction. But an isogeny is given by its kernel, and there can be up to L+1 isogenies, because there can be up to L+1 cyclic subgroups of size L for any elliptic curve. And so we need slightly more refined analysis. And so Tay showed that if you have 2 elliptic curves over a finite field are isogenous if and only if they have the same number of points. In particular, their traces are the same. Well, and that means that their endomorphism rings both contain the same order, z adjoint pi, because pi is the root of x squared minus tx plus q. Okay, and then came Kohel, and he refined that if you have an L isogeny between 2 elliptic curves, then you know what's happening with the endomorphism rings. They either have the same endomorphism ring, which is the situation we were before, or the first endomorphism ring contains the second endomorphism ring with index L, or the second endomorphism ring contains the first endomorphism ring with index L. In the first case, we call the isogeny horizontal. Here it's descending, here it's ascending. Okay, and there's a beautiful way how to visualize this. So we define another isogeny graph and calling this the component of E. And what we're trying to do, we're trying to capture all the elliptic curves that we can reach from E using only L isogenies. Okay, so the vertices are FQ isomorphism classes of curves that are L to some power isogenous to E, and the edges are again L isogenies. And what we get a volcano. And what this means is that there is some very, very beautiful structure. One of it is that there is a cycle on the surface, which is the top. Okay, let's start over. If you have a volcano, you have a partition of the vertices in the graph in such a way that the last set forms a cycle. The first set forms, if you just look at the subgraph generated by those vertices, then you only get isolated vertices. So the top is called the surface, the bottom is called the floor. The isogenies that go from the surface to the floor are descending. So in the definition as before, the isogenies that go from the floor to the surface are ascending. And you know that every elliptic curve on the floor has the endomorphism ring, which is exactly equal to Z adjoined with pi. So it's the smallest possible endomorphism ring any elliptic curve over FQ can have. Okay, and then there's some condition on neighbors. Okay, and what I want to say about this is that these volcanoes are beautiful. They have this very rich structure, and the way how the elliptic curves are layered in the volcano just really depends on the endomorphism ring. So on the floor, you have the elliptic curves with the smallest endomorphism ring, which is the Z pi. And then from the floor, you can only go up. So you take ascending isogenies and you get larger and larger orders. But every ascending isogeny gives you a larger order of index L. So where your endomorphism ring sits in with index L. So in other words, the levels of volcanoes can be labeled by orders, by sequence of orders, with each of them is with index L in the next. Okay, but this actually gives you, if you want to have a large volcano, then you want to have a large power of L dividing your discriminant, and that's kind of difficult to arrange. Typically, you would see very, very modest volcanoes. So for supersingular elliptic curves, the best you can do is a volcano with 2 layers, but it can only be a 2 volcano with 2 isogenies, and typically for supersingular elliptic curves, all these volcanoes will just be cycles. Okay, so we finally get to the case where the quadratic equation for Frobenius has discriminant 0. So what does it mean? This quadratic has a double root, and you can show that in that case, the Frobenius will actually act as a plus minus square root of plus minus square root of q minus q. Sorry. Anyway, the thing I want to say is that the trace it needs to be equal to plus minus p to n over 2. Okay, so if the discriminant is 0, then you have this information about the trace. And since the trace is a power of p in this case, it's obviously divisible by p. So this is the case only for supersingular curves. And from what I told you about the endomorphism rings, is that in this case, the endomorphism ring is a maximal order in a quaternion algebra ramified at p and infinity. And there are some mixed blessings coming out of this. Well, depending on who you ask, it's a positive or a negative fact that quaternion algebras are non-commutative and just more complicated, so their arithmetic is just more difficult to describe. The good thing is that you can still construct isogenies from ideals. But in this case, even if you have invertible ideals, even if you, like, no matter what conditions you put, you will not get the same endomorphism ring. Okay, so for imaginary quadratic orders, we had this thing that if you acted by invertible ideals, you always had the same endomorphism ring and the same trace. This is no longer true for quaternion algebra. For this case, for when you live in the quaternion algebra. There's a good or a bad thing, but there is also no class group for quaternion algebras because it's non-commutative, so you only get a class set, so there's no group action. The bad thing is that you can't just repeat the Diffie-Hellman square. The good thing is that there is no sub-exponential attack on this quantum attack. So potentially there could be like more security coming from these elliptic curves. And another great thing about supersingle elliptic curves in this case is that they all have J invariance in FP squared. And so everything we need to consider is just the case where Q is P squared and the trace is minus 2P. Okay, so this long slide just ends with the following. We have a supersingular elliptic curve defined over FP squared with trace equal to minus 2P. And now let's try to say something about the isogenies of these curves. Okay, so you'll get as an exercise to show that the group of rational points over FP squared is isomorphic to 2 copies of Z mod P plus 1Z. Okay. So what this means is that there's either no L torsion or there's full rational L torsion. And in this case, if there's any L torsion, there's full L torsion, then just looking at the order of this group, which is P plus 1 squared, you see that L needs to divide P plus 1 squared. Okay, so we're just going to stay in this case where we have some L isogenies, and so we take some prime L that divides P plus 1, and so we're going to define yet another isogeny graph. And so this is going to be the supersingular L isogeny graph, where vertices will be supersingular J invariants in FP squared, and edges will be L isogenies, again up to equivalence, because here we identify elliptic curves up to isomorphisms, and we will also identify dual isogenies, again because going there and going back only gives you this boring multiplication by L. Okay, so this is a supersingle isogeny graph. And so here we have some pictures, and as you can see, it looks nothing like the graphs that we saw before. Okay. And it's not just because I didn't draw it nicely, but you can see you have some loops, you have some cycles. Every now and then there is a double edge. So this is the 2 isogeny graph. This is the 3 isogeny graph over this field. So you see here you have a double edge. Here you have 2 loops, and there are just lots of not too small cycles. Okay, so these graphs are just very different from the graphs that we saw for the commutative case, where we were just in an order in an imaginary quadratic field. So what are the properties of this graph? Well, there are some things that you can prove. You can prove that this graph will have about P over 12 vertices. So they are very, very large graphs. And for cryptography, you will have P that has maybe 100, 150 digits. So imagine a graph that has that many vertices. What is also interesting is that these graphs will be connected. So remember with the seaside graph, it was possible to just get a bunch of cycles for the action of L isogenies. But here, these graphs are connected, so you can connect any two supersingular elliptic curves defined over fp squared by a sequence of L isogenies. They are also L+1 regular, so this, with possible two exceptions, but this means that from any vertex, there are exactly L+1 edges. Okay, and this is in line with the fact that every supersingular elliptic curve has the full L torsion, which means that there are L+1 different rational L isogenies. Another thing you can prove is that they have these graphs have rather short diameters, which means that if you take any two vertices, the shortest path between them will be rather short. You have a graph that has p vertices, but the shortest path between any two of them is about the size of log p, just very, very small. And you can also prove that these graphs mix rapidly, which is the following. I choose a vertex, and I take a random walk. And this random walk gives me some endpoint, and I can look at this distribution of these endpoints. And provided that I take a random walk of fairly short length, just about log p, the distribution of the endpoint vertices is very close to the uniform distribution. So I can just sample randomly from the graph just by taking random walks. Or in other words, if I just take a random walk, the vertex that I get just looks very random. And this is a great property for crypto. And so all the first 5 things, there are things that you can prove. They're not extremely hard. But the 6th point is that conjecturally, they're also difficult to navigate, which means that if I take 2 arbitrary vertices, then it is difficult to find a path between them. And this is a problem that is currently exponentially hard. And so what do I mean by it? You have a graph that looks something like this, and you just choose some 2 vertices in there, and you look at what, your task is to find any path between these 2. Okay, so you can get a moment to figure out the shortest path between these 2. Okay, no volunteers? Okay, so it's this path in red. Okay, and now imagine doing this on a graph that has just 10 to 150 vertices. This is a graph you can't even write down. Okay. Right. So pathfinding on these graphs seems to be difficult, and so this is where we reach crypto again, and this is what the supersingular isogen Diffie-Hellman does. I'm not going to tell you exactly what the protocol does, but it is a Diffie-Hellman-like protocol. So you again have Alice and Bob trying to end up with a shared value. And I'm gonna explain to you what Alice does. So there is some starting curve, and Alice chooses some random sequence of L isogenies. And so in the end, she just obtains, if she composes these L isogenies, because degrees of rational maps multiply, she ends up with the composition will be a isogeny of degree, some large degree L to E. Okay, and so her secret will be the path in this isogeny graph that gave her that gave the isogeny, and her public key is the N curve. Okay, and the advantage of SIDH is that the fastest stacks are exponential, both quantumly and classically. It's very easy to instantiate this using just 2 and 3 isogenies, so isogenies that are very, very quick to compute. And this rapid mixing of the isogeny graph tells you that if you take a random path, then you end up with an elliptic curve that just looks uniformly random. So it looks like these public keys are just uniformly random. And so it's a really cool protocol. Except if you actually instantiate it, then you end up with these like very mind-blowing things that happen. And that's that this pathfinding that I told you about is not actually hard for all vertices. It's easy to find paths, or it's easier to find paths between curves if their J invariants are not in FP squared but in FP. It's easier to find paths if you know the endomorphism rings. For the actual instantiation, Alice needs to publish auxiliary data along with the endpoint, along with the elliptic curve. And this gives you active attacks. So you only get passive security, which is enough crypto, but you still get active attacks. You get attacks that exploit this auxiliary data and be it unrealistic variants, but some variants of this setup. And also the length of Alice's walk is just way too short, and also Bob's walk. Their walks are just very short, so they're too short for the rapid mixing property. So you don't really end up with a uniformly random public key. And you're not even taking advantage of the full graph, the subgraph that like all the isogeny, like all the elliptic curves that are ever reachable by the protocol that generates Alice's public key. That's just going to look like a tree. So you have this beautiful isogeny graph with this provable, very desirable properties, and you end up taking what almost looks like a tree. Here, if you start from this point and you don't take the full length, then you actually end up with something that maybe has some cycles in it, but there are parts that definitely still look like a tree. And what's even more impressive is that none of these issues actually break the practical instantiations of SIDH, or the most the best implementation, which is Psych, which deals with this passive security. But none of these issues have any impact on the security of this. And I think this is a good moment to stop.